Greetings everyone, this is OpenSpace. I'm using my cursor just to show you that I'm actually some of the motions that'll be subtle but flying in over Mars, over the Valles-Marineris system. And we're cutting over from IS Chasma into Western Candor Chasma. We're looking at results from the Mars Reconnaissance Orbiter over terrain that is not exaggerated. Terrain here was created as a mosaic of CTX camera, which is 5-meter resolution globally. Do stereo analysis of that by my high school students from Bergen County Academies. And we're coming up into a high resolution area, even higher resolution, 25 centimeter resolution from the high-rise camera in Western Candor Chasma, just southwest of Seti Mensa. And so we are seeing wind sculptured terrain here on the order of a few hundred meters, these hills that we see. The layering is exposed, almost looking like wood grain. And then we can also see smaller infill of sand dunes that have been blown around. The atmosphere is a physics-based atmosphere made for the OpenSpace software. OpenSpace can be obtained for Mac and for Windows, as well as a Linux install that you'd have to compile it yourself. But from the website, freely available. It's open source software called the website OpenSpaceProject.com. And I'm flying this here at the American Museum of Natural History. We're one of NASA's Science Activation Group partners, funded by the Science Mission Directorate at NASA headquarters. And so this is meant to be free and open for the entire world to use. The objective here with showing planetary surfaces at high resolution is to really be able to put together data sets one on top of the other to show them in context. And so here we've nested the high-rise terrain modeling with the CTX terrain modeling, which I mentioned was done by my high school students using a process called the NASA Ames stereo pipeline that is also available, free and open. The canyon walls that we see here are on the order of 5 to 7 kilometers or so. So think about 20,000 feet, whereas here we have these hills down here, which are on the order of a few hundred feet tall. Altogether, there are over 500 processed high-rise terrains at this high-resolution, 25 centimeter, about 10 inches resolution. This camera was put in service to verify the safety of landing sites for Mars rovers, and well, in particular, the Mars Reconnaissance Orbiter was looking at the terrain that the Curiosity rover and the future Mars 2020 rover will hopefully also land successfully in. Once again, there's no vertical exaggeration here. We're showing this properly in context of elevation. And the coloration is based on a global color that is inherited over the inherently monochromatic images that we see in front of us. The high-rise terrain modeling was also done by multiple imaging, in the case of 2 stereo pairs, and were processed by graduate students at the University of Arizona, where this camera is managed under principal investigator Alfred McEwen. So while these high resolution sections are small in comparison to the region around them. Once again, they hold a lot of information for the geology of these specially targeted regions. Surrounding it is the 5-meter terrain. And we're happy to be displaying here the image of a global CTX 5-meter terrain that is being processed by Jay Dixon of Murray Labs at Caltech. And he has pretty much seamlessly blended coverage from over 10,000 orbits over 10 years, actually, I think 50,000 orbits, if I've got that right. And about 98-99% coverage of Mars. So it doesn't have exactly just everywhere. There are a few holes, but as you see here in the canyon area and coming out to fly over these mounded sediments in the middle of western Candor, we can see the canyon surrounds. The wall rock is volcanic layers that have been exposed, and you can also see the result of slumping. We're streaming the high-resolution maps from our OpenSpace server. In this case, in Utah, we have a mirror site at Linköping University in Sweden. We fly forward toward this area. I'm headed north-northeast. Over this rather beautiful terrain of western Candor Chasm.
Okay, be right there.
We're doing our very best to portray Mars exactly how it was seen by the spacecraft, and the terrain modeling without vertical exaggeration is displaying a proper landscape as viewed from where we're flying in open space. I'm using a mouse to essentially, if I move the cursor, we'll see it comes down. I'm sort of drawing the mouse toward me with the left mouse button. It allows me to, with friction off, just sort of seamlessly glide over these areas. You can see wind-carved longitudinal features, yard angles created by the winds in this area. I'm flying toward sort of an erosional remnant out in front of us. And then beyond that, we see the walls of northwest Candor Chasm, and also the slumping terrain from the recession of the canyon from fracturing and slumping. My altitude is adjusted by using the right mouse button, and I have friction toggled off for both the sort of orbital action, which is my left mouse button allows me to sort of move around, and then middle mouse allows me to turn like so. And if I want to go higher, I pull the mouse toward me or push the mouse away from me for up and down action, vertical action. My name is Carter Emart. I'm a co-investigator on the OpenSpace team. The software started as a project between myself and Anders Ingerman, professor of computer graphics at Linköping University in Sweden, in the town of Norrköping. Anders is one of the world's leaders in computer graphics and data visualization research, and his students had helped us in the creation of everything in OpenSpace that is available. We're just seeing Mars, but we visualize the entire digital universe, which is a compendium of astronomical catalogs that the American Museum of Natural History has put together. Brian Abbott and myself working on that since 20 years plus here at the museum. Um, and but the result of what you see here to model the surface was done by Eric Brabard and Khalid Ladin as a dual master's thesis from Linköping University. They're both Swedish, and they added this functionality using GDAL, the geospatial data abstraction language, which is what we use to interactively then fly over this. Our core developer, Jonathan Costa, on the OpenSpace team, spent over a year putting in physics-based atmospheres for planets in general. We're applying the proper Rayleigh scattering coefficients to give you the type of scattering that you're seeing here. Flying over this hummocky set of hills from the massive landslide occurring coming off the wall rock that you see here along northern Kandor Chasm. The particular processing and mosaicing of the terrain models that we're now flying over, which is the 5-meter CTX Ames stereo pipeline processed data, was done by Janie Levin and Chiara Ferrari Wong, both Columbia students, but Chiara graduated and is now a second-year graduate student on her PhD track at the University of Hawaii in lunar research. Janie is finishing up Columbia, but together they were my students formerly from the Bergen County Academy's high school, which is a highly achieving high school in the New York tri-state area, located in Hackensack, New Jersey. Coming up and over this sort of mesa area, which is really just the border between Kandor Chasma and Ophir Chasma to the north. We'll just come in here and just investigate a little bit more of this canyon area that is covered by the higher resolution mosaic. The data is streaming. I think we're also seeing a limit over to the left, a boundary region between the height models, high resolution to the right, lower resolution on the left. The lower resolution on the left is MOLA, which is the Mars Orbiting Laser Altimeter data, which is only as good as a couple hundred meters or about 400 meters at the equator. Whereas the CTX stereo processing gets us down to as good as perhaps 20 meters per pixel. Much finer resolution. The image itself is about 5 meters. So sometimes I have to kind of pause to let the data catch up in the streaming of the data. And what we're seeing down below us, we can see the valley of this canyon, but we also see the toe of what looks like the flow of a glacier. It's covered with the Martian red dust, but the form sort of belies that underneath it is perhaps a glacier or rock glacier that's been flowing down the canyon and spreading out as a toe. Either glacial action or perhaps a debris flow from collapse in this canyon at an earlier time. Come around here, we see a nice sort of wall exposed out in front of us. We'll fly along that and then continue going north. We're going about northeast right now. Once again, Ophir Chasm. OpenSpace has been developed really with the idea of immersive projection spaces, the Hayden Planetarium, also the domed theater at the Visualization Center in Norrköping in Sweden. Once again, our colleagues and where the talent of the students come from in the curriculum based on data visualization and advanced computer graphics. Our informal science institution partners for the OpenSpace grant from NASA include California Academy of Science, Marsden Planetarium, the Gates Planetarium at the Denver Museum of Nature and Science, Adler Planetarium in Chicago, and also the Burke Baker Planetarium at the Houston Museum of Natural Sciences, and the North Carolina Museum of Nature and Science, or Natural Sciences. I think it's Nature and Science in Houston. North Carolina does not have a planetarium per se at the Museum of Natural Sciences, but Rachel Smith, who's our co-I on that, has a visualization lab, and so they use OpenSpace and have students make movies with it, use it for education, and it's a quite flexible tool used in classrooms to demonstrate things such as we're doing now, or the relationships and motions of the planetary bodies in the solar system. Mission visualization. Also, we concentrate on solar or heliophysics and space weather on Earth's magnetosphere, thanks to working with the Community Coordinated Modeling Center at NASA Goddard, as well as astrophysical simulations. I mentioned that the digital universe is this catalog of stars and other objects that make up the Milky Way galaxy, and then beyond that into galaxy databases such as the Sloan Sky Survey, and so that we can really put together what we know, what we've investigated of the entire universe, and visualize it by putting all the data together into OpenSpace. I'm starting to head south, going a little bit higher up, and here across the division into Candor Chasma once again, where we had started, and there's a deposit of layered sediments that actually extends across the sort of mountain range dividing these two canyon areas. We have a spectral signature of sulfates, sulfur coming from what was outgassed by the volcanoes. And so in these sediments are similar in composition and deposition to what we see in Gale Crater, where Curiosity is on the other side of the planet. Large crater with a mound of sulfates that are actually higher than the rim of that particular crater. So these sediments are quite large. We still debate over the origin of them. However, what we see here is laid down in such a way that the erosional features that we see here, these sort of fluid channels, are typical of the erosion of the layered sediments. Well, this gives you a taste of what we can do in OpenSpace. So thanks for joining. If you've seen this and there'll be other sessions like this to come. Thanks a lot.